So in today's lecture, we will discuss about the piezoelectric material which are used in sensors and actuators. So most materials have physical properties which are difficult to alter. However, there exist some materials whose physical property can be significantly altered. One such material is known as piezoelectric material. Piezoelectric materials are widely used as sensing and actuating elements in various applications, because their physical properties can be changed. This section describes two important properties of piezoelectric material. One is the piezoelectricity and another one is the piezomechanics. So here one figure is given where different parts of a capacitive pickup base sensor is shown in figure number A, which shows a probe, oscillator, rectifier filter, and output circuit. In figure number B, it shows a capacitive MEMS sensor with electrode and substrate. So coming to the first property, piezoelectricity. Piezoelectric materials are permanently polarized crystalline materials. If their dimensions are changed as a result of mechanical force, electrical charges proportional to the imposed force are accumulated on the surface upon which the force is imposed. So the figure 5.9 shows that the piezoelectric effect, when there is change in the dimension due to the force or pressure applied on a particular surface, then charges are accumulated on that surface proportional to the imposed force. The overall crystal remains electrically neutral, but displacement of charge center results. The phenomena is known as the piezoelectric effect or piezoelectricity. This was originally studied by the Perry and Jacques Curie in 1880. Some of the piezoelectric materials are ammonium dihydrogen phosphate, barium titanate, lead betanabate, lithium sulfate, polyvinylidene fluoride, PVDF, Rochelle salt, tourmaline, quartz, and zirconate titanate. The Greek word piezo bears the meaning of pressure. The property is exploited to measure many physical parameters such as pressure, force, strain, torque, acceleration, sound, and vibration. The relationship between the applied force and the charge accumulated is given by Q is equals to Cf, where F is the applied force, Q is the accumulated charge, and C is called the piezoelectric constant. The piezoelectric constant is not actually a constant, rather the value depends on the orientation and the mode of operation. Orientation and mode of operation refers that orientation means by which the transducers are cut from the original crystal. Mode, the way by which the stress is applied. So these two things are considered. One is the orientation and the mode of operation for the selection of the constant, piezoelectric constant C. Piezoelectric transducers are cut from the crystal slabs or plates in a specific orientation with respect to the crystal axis, depending on the application requirement. There are mainly four types of cuts, namely longitudinal cut, transverse cut, shear cut, polystable cut. So because of these orientation, the C value varies. The shear cut is commonly used for force and acceleration measurement, such as, whereas polystable cut based transducer are applied for pressure measurement. So this cut type or orientation type depends upon the type of application where the piezoelectric material will be used. Various modes of operation are bend, shear, and compression. When the force is applied, it is in the bending direction or shear direction or compression direction. The charge in a piezoelectric transducer is therefore proportional to the piezoelectric constant of the material and to the stretched or squeezed force. During operation, the piezoelectric transducer can be thought of as a parallel plate capacitor, which is shown over here in figure number 5.0, where there are two plates with a dielectric medium. A is the surface area of the plate on which force is applied, and T is the thickness between the two plates. So the value of the capacitance is given by Cp is equals to epsilon r epsilon naught A by T, where Cp is the piezoelectric capacitance, A is the area, T is the thickness of the transducer, epsilon r is the relative permittivity of the piezoelectric material, and epsilon naught is the permittivity of the free space. The capacitance can be expressed in terms of charge accumulated per unit area or per unit voltage, which is given by Cp is equals to Q by V, where V is the potential difference between the plates. Now on combining equation number 5.6, 7 and 8, we'll get that capital V is equals to Kf, where K is equals to Ct by A epsilon r epsilon naught. Thus, from this equation, it can be noted that voltage is proportional to the imposed force, that how much amount of force is applied on the piezoelectric material, then the same amount of charge can be generated. The potential difference V is very weak. Usually the voltage is amplified by using a amplifier. We have earlier studied that with some transducer we have to use a signal conditioning devices. So here the same signal conditioning device is talked about as amplifier. Amplifier used for this purpose is referred as charge amplifier due to the reason that the accumulation of charge effectively appeared as a difference in the potential across the material. So in the upcoming figure 5.11, it shows an equivalent circuit of a piezoelectric transducer which is coupled with the charge amplifier. The circuit can be considered as this. So here you can see a transducer circuit, then a cable circuit, then a change amplifier. So there are four sections: the transducer, the cable, the charge amplifier, and the display unit. RP, RC, and RF are called the leakage resistance, cable resistance, and feedback resistance respectively. CC and CF are the cable capacitance and feedback capacitance respectively. A is the open loop voltage gain of the charge amplifier. So such block diagrams are very important when you will explain this piezoelectric material. So this will help you to clarify your answers. Now coming to the another property, piezo mechanics. Piezoelectricity is a phenomena which implies that electricity is generated by applying force that causes mechanical deformation to any piezoelectric material such as a PZT, ceramics, lead, zirconia, titanate. However, reverse phenomena is also possible, which implies that when such material are exposed to some kind of electric fields, then mechanical deformation takes place. That is, the shape of the material changes. The effect is complementary to the same piezoelectricity. The amount of deformation is proportional to the applied electric field. And this phenomena is known as piezomechanics. The simplest piezomechanic component can be designed by forming a PZT, that ceramic layer, that means lead, zirconia, titanate layer, and applying a potential difference across each side of the layer as shown in the upcoming figure. So I'll show you the figure over here. And now I'll explain that it is a mono layered PZT component. The PZT components are also called moving capacitors. The monolayered PZT component can be used as an actuator. Actuation is a process of conversion of energy to mechanical form. So here the electrical energy can be converted into mechanical form with the help of such piezomechanic material or a piezoelectric material which are utilizing piezomechanic properties. A device that accomplishes this conversion is termed actuator. Based on the geometrical configuration, logically there exist two types of deformation or effects. They are denoted as D33 and D31 effects. The D33 effect is characterized by the deformation as shown in this figure A, which is a deformation in the direction of the applied field. You can see that the field is applied in the upward downward direction, so the same D33 deformation is produced in the same direction. Without loss of generality, it can be convinced that because of this D33 deformation, there must exist a negative deformation, that is shrink in another direction called in plane direction. So with every action there is equal and opposite reaction. So with every positive deformation there is associated negative deformation. The in-plane deformation or shrinking is characterized by D31 effect. The mode of operation due to D33 and D31 effects are called thickness mode and planar mode respectively. The thickness is governed by the physical property of the material, which is eventually reflected through its mode of operation. The above deformations correspond to two types of coefficients such as D33 coefficient and D31 coefficient respectively. The deformation is not only proportional to the applied electric field but also to the D33 coefficient. If it is operating in D33 mode, multi-layered PZT component can also be designed to operate in the D33 mode. Now this figure number B shows multi-layered PZT component in which piezoelectric layers are stacked. Planar type piezoelectric microactuators has a sandwiched structure which is shown over here in figure number C. The shear mode effect are shown in figure number E. A typical spring type piezoelectric actuating components is shown in figure number D. So there can be different mode of operation, there can be different ways of orientation. So in figure number A we studied about the monolayered piezoelectric component, in figure number B we studied about multi-layered, then figure number C is planar type sandwich, figure number D is shear type horizontally polarizes, and figure number E a typical spring type piezoelectric material based on micro actuator construction. Now in the upcoming lecture we will discuss about the MEMS gyroscope. Thank you.